Hello, everyone. Welcome to another wonderful day of chemistry. So today we're talking about the Henderson-Hasselbalch equation, which really, despite its weird sounding name, is a way to talk about how the pH of a system relates to the strength of a weak acid-base pair. So what we're really seeing is that if I end up mixing together a weak acid and a weak base, what we're going to do is generate something called a buffer. And the reason why it's called a buffer is like anything that buffers a system, like your computer buffering, what we're doing is essentially modulating a change. We're slowing down the change of any sort of acid or base to the system. And we'll investigate this in much more detail next lecture. However, for now, what I really want to focus in on is how we can go ahead and calculate the pH of a system as long as I know the concentration of both the weak acid and the weak base for the system. If I know this ratio, I can determine the pH of the solution. And so really what's going to make this whole relationship work is, as we saw last time, the amount of protons being released from a mixture of weak acid and base is going to be very small in compared to the actual amount of both of those species present. So as long as I have a sufficient amount of weak acid and a weak base pair present, what we're going to see is that any release or gain of protons from just the water surrounding is going to be very minimal. And so what we can do is calculate the exact pH of a system using the acid dissociation reaction and its equilibrium constant. And most of what we're going to do from here is just some cute mathematical tricks. So what I can do is say, hey, I've got a Ka, and it's going to be related to this ratio. Now, like most cute mathematical tricks, it starts with a log. So what we do is we take the negative log of each side. So I've got the negative log of Ka, and I've got the negative log of the ratio. Well, it turns out we know what the negative log of Ka is. It's Pka. Then I can go ahead and use log laws to say, hey, the log of a product is going to be the sum of the logs. So negative log of the whole equilibrium constant is going to be the same as negative log of the ratio minus log of just the hydronium concentration. So I'm going to pull that hydronium concentration out on its own, because turns out negative log of the hydronium concentration, well, that's just pH. So all I'm left with is negative log of the ratio of the concentration of base over the concentration of acid. And it turns out what we find out is that we can find the pH of a system as long as we know the pKa and the log of the ratio of base over acid. And this whole equation is known as the Henderson-Hasselbalch. And it essentially ends up showing that the pH only depends upon the ratio of base to acid, because for a given acid-base pair, the pKa will be fixed. And oftentimes it's useful to keep in mind how I can make sure I'm using the right ratio, and that again, it's base to acid, not acid to base. Good way to think about this is that if I add more base, my pH should go up, as it should be more basic. And so we can make sure that if I increase the base, log of that ratio will go up, and so the pH will go up. So this will help as a good useful reminder of how the Henderson-Hasselbalch equation essentially works. Now, one of the big things that this is used for is if I have a known mixture of acid to base, I can find out the pH of that system, which is very useful if I'm, say, mixing together acetic acid and acetate, or benzoic acid and benzoate. We've seen a lot of these very common acid-base pairs. Conversely, if I know the pH of the system and I know what acid-base pair I'm working with, I can figure out the ratio of this conjugate acid-base pair just from that ambient pH of the solution, which is also incredibly useful. However, it is worth noting that the Henderson-Hasselbalch equation does have certain limitations. It's going to hold the best as long as this ratio is essentially between 10 to 1 acid to base and 1 to 10 base to acid. So again, as long as this ratio is essentially in between 0.1 and 10, this equation holds fairly well. And it will even hold decently well for about 1 to 100 and 100 to 1. The issue is, past this point, we run into problems with the fact that we assume that the amount of hydronium released or consumed was fairly low. If the either concentrations or that ratio gets a little too small, we can run into some problems. So as long as we have a significant amount of both acid and base present, the Henderson-Hasselbalch equation, though, will work very well. So let's go ahead and see how this Henderson-Hasselbalch equation actually works. So let's take one of these scenarios where we've got a mixture of 0.1 moles of acetic acid and 1 mole of acetate. So again, here's a good 10-to-1 solution. So we can kind of see where the Henderson-Hasselbalch equation takes us. So if I'm looking at acetic acid, it has a pKa of 4.75. So I can go ahead and plug all these numbers into the Henderson-Hasselbalch. I know pKa. Now the problem is I don't actually know the concentration of acetate and acetic acid. I know the moles and volume. So let's go ahead and plug in those values. And here's the important thing. As long as I have the same volume of both species, that 10-to-1 ratio stays constant in both moles or molarity. So as long as you know the moles, the Henderson-Hasselbalch equation should work. However, if you're unsure whether it's better to use moles or molarity, use molarity. It's how the equation is designed to work. So I can then go ahead and plug in these two molarities and my pKa. So I've got a pH of 4.75 plus the log of, again, I've got more base than acid, so it's going to be the log of 10. Now, very useful thing when we're using the Henderson-Hasselbalch, as I said, it works very well if that ratio is somewhere in between 10-to-1 and 1-to-10. This is going to be the same thing as the log of 10. 10-to-1 is 1, and the log of 1-to-10 is -1. This means the Henderson-Hasselbalch equation holds very well within essentially 1 pH unit of the pKa. So again, if I've got the ratio of acid to base fairly constant, it's going to keep it within 1 pH unit of the pKa for that system. In this case, since I've got more base than acid, it's going to be a little bit more, it's going to be a little higher, a little bit more basic with a pH of about 5.75. Now let's go ahead and use the other version of this. So it turns out Windex contains a mixture of ammonium and ammonia and ammonium, but ammonium is mostly present as ammonium hydroxide, but for our purposes, that really won't matter. And it turns out that it tends to have a pH of 9. And a very common total molarity for this mixture of ammonia and ammonium is 0.85 molar. Now the issue is that I'm not sure whether it's mostly present as the base form, ammonia, or as the acid form, ammonium. Hard to tell. The fact that the pH is less than the pKa probably means I've got a little bit more acid than base, but let's go ahead and try and figure out the exact molarity. So first thing I'm going to do is set up my Henderson-Hasselbalch. It's going to be my pKa, have that, and the log of the ratio. Now the issue is this gives me two unknowns. So the best I can do here is solve for the ratio. So the log of the ratio should just be the pH minus the pKa, which in this case turns out to be -0.25. I can then say that, hey, the ratio of base to acid is going to be 10 to the -0.25, which it does turn out is indeed a positive number. It's about 0.56. So this means that for every 1 mole of ammonium, I'd have about 0.56 moles of ammonia. This only gets me so far. So what I can do is use this second piece of information, that the combined molarity of ammonia and ammonium should be 0.85 molar, which means the ammonia concentration should just be 0.85 minus the ammonia. I can then go ahead and insert that back into my ratio. And it turns out that this means that my concentration should be, my ratio should be 0.85 minus ammonium over ammonium equals 0.56. Ooh, this seems a little heavy. But with a quick little algebra fix, I can get rid of my denominator and then pull my ammonium over to the other side. So now I've got a molarity equals a ratio times my ammonium concentration. Then solving for ammonium, we find that we do indeed have an ammonia concentration of 0.54, and then plugging back into here, an ammonia concentration of 0.31. So just like our original instinct said, if the pH is below the pKa, we have a little bit more acid than base. The rest is algebra, mostly to figure out the exact ratio, and then use that ratio to do something useful. So next time, we're going to go ahead and see how a buffer can be used to essentially slow the change of pH in a real chemical solution. Until then, take care.